Okay, let's start. Good morning and welcome back. So we were discussing this particular topology. This is not required right now. Yes. Can you speak a bit louder? Right. Correct. Right. Right. Sure. I'll go through that. Okay. So a quick recap of this is assuming that this can be biased. So there was one question even in last class. There was slight confusion in the sense that I made a comment on what sets the current in this stack. Given that this is biased to a constant current source, one might argue that this constant current source is the one that is setting the current in the stack. Yes, indeed, but the question is not meant for that. The question essentially what I am trying to ask is, given that there is a constant current source, which transistor in this stack is responsible for absorbing if there is a change in current? For example, if I0 for some reason changes to I0 plus delta I, which transistor will be responsible to ensure that that this current gets absorbed without while ensuring M2 and M1 are in saturation? M1, right? Because ultimately the knob is VGS, and if the VGS of M1 changes, in this case, if VGS of M1 increases, then obviously it will be able to absorb the current. And if it is a constant current, since it's a constant current bias, the VGS of M2 will also change. But note that this source voltage, since the gate voltage is constant, the source voltage will adjust itself. This is, as far as M2 is concerned, this is equivalent to feeding, taking current. I mean, this is equivalent to saying that if this node, since the gate of M2 is fixed, this node can move. If this node moves, if this node moves, then the current will get auto-adjusted. But that is a consequence of something happening. That is not the cause, that is the effect. Right? And the effect is happening because if there is a change of I0, the gate voltage, the VGS of the VG of M1 increases. Since the VG of M1 increases, this current through the transistor stack also balances and increases. And because of that, the source of M2 changes. Okay. So that is the argument. Now, once you are convinced with the argument, you have to do an analysis and see, to start off, you have to ensure that these transistors are in saturation. If they are not, then whatever we are doing has no meaning, because ultimately we would want to design amplifiers or use it as a bias circuit for some other amplifier and so on. So the quick calculation that we did was, let's assume W by L. So correct. Right, correct. But I mean, that is regardless, right? Because there is no other other path through which I0 will flow. So I0 will regardlessly, whatever happens will flow through M2 and M1. But if they are not biased properly, one of the two following things can happen. That is, either this voltage can go up and crush the current source, or this voltage can go down and then crush M2. I crush M2 as in it might push M2 in linear region, right? So we want to prevent that from happening. So given that I0 is flowing through this stack, we should ensure that the biases are set in such a way that none of these two situations arise. Okay. So if that is the case, then we have to go and the tried and tested method that let's assume that it's in saturation and see whether that possibility, that is one of the possible solutions. If that is a possible solution, then we are happy, then we'll bias, we'll size the transistor accordingly. And if that is not even a possible solution, then move on to something else. Okay, so now the easier way to go about doing this is more convenient way. I won't say easier also. The more convenient way of going about doing this is expressing. Ultimately, we are trying to fit all these node voltages are some form of VGS or some voltage minus VGS or some voltage plus VGS and so on. So for a given constant current source, for a constant current bias. So essentially, I can say I can use this expression all the time. For any of these transistors. Now, depending upon what is the WIL, what is the VTH, the values will change, but this is essentially what is a very useful way of going about analyzing this. And given that this part is V overdrive, I will just call it as V overdrive and use this going forward. Now, we note that V overdrive, VTH is not a design parameter, but by design parameter, I mean VTH you cannot tweak to a large extent, but V overdrive you can tweak, because V overdrive is a function of W over L. Since you can change W over L, you can change V overdrive. You have to increase V overdrive of certain transistor, you have to reduce W over L, and if you have to decrease, you have to go in, if you have to decrease the V overdrive, you have to increase W over L. And that is a very useful parameter that you can have in your back pocket in order to bias, move certain voltages up and down. Also, I mean, one might argue that the I0 is also a design variable. Yes, it is a design variable. However, in a constant current bias, you are essentially starting off with the assumption that I0 is given, and that is not fixed. Okay, so so now given that this is what it is, how do I go about analyzing this? Let's you have to start off as somewhere. The starting point that we assumed in the previous class is, let's assume that M2 is just at the edge of saturation. If that is the case, we'll just go around the loop and see whether that condition can be satisfied. If that condition is satisfied, we'll try to then take M2 away from the edge. Right. So that's essentially what we are trying to do. So if M2 is right at the edge, then I can say that this voltage is what this voltage is. No, let's not go that way. Let's go this way. So M1, the gate to source voltage of M1 is threshold voltage plus V overdrive of M1. Right. So this is connected to this node. So this node is also threshold voltage plus V overdrive of M1. If M2 has to be in saturation, then what is the maximum VB that I can have? This will be higher or lower than VTH plus V overdrive? Maximum VB. Yeah, so one threshold voltage higher, right? Gate can go one threshold voltage higher than drain while keeping transistor in saturation. So this will be 2 VTH plus V overdrive 1. So if that is the case, what will be this voltage source of M2? Let's assume different WL and we call that overdrive V overdrive 2. So this is essentially what? This is the VB minus VGS. Correct? This is VB minus VGS. So VB is 2 VTH plus V overdrive 1, and VGS is VGS of M2, that is threshold voltage plus V overdrive 2. Right? So this is threshold voltage plus V overdrive 1 minus V overdrive 2. Okay. So now you have all the relevant node voltages in terms of threshold voltages and overdrives. Which one can you call out? The gate or source? Which one? Source of M2. Okay. So what is source of M2? Source of VS2, let's say, is VB minus VGS of M2, right? And this is VB is whatever we had, and VGS is, again, I'll use this, threshold voltage plus V overdrive. Correct? So now if you have this, if you arrive at this situation, then now it's easy to see what condition needs to be satisfied in order to keep my transistor in saturation. So to start off, we assume that the way we have biased it, M2 is just at the edge. Now, how do we know if is M1 in saturation or not? Yes. No, right? I am. You mean this one? No. Why? I am. What? So who is okay? So this is important. Who is setting the source voltage of M2? Correct. Yes, the top one is overdrive one. That is fine, because who is setting it? For example, setting it where? Correct. Right. That is getting set by M1. But who is setting the source voltage of M2? Exactly, right? The gate of M2 is fixed. The current is fixed, which means the source voltage will be gate minus the required VGS for the same current. Right? So that's what is happening here. So this is VB minus VGS, VB minus VGS of M2. And VGS of M2 is threshold voltage plus overdrive of M2. Okay. Okay, fine. So now how do we just started off. You need not consider. I mean, you can then start off with saying that this will be any random values. Then I'll get some limits on dB. Then we'll see what impose another condition. Yeah, right. Okay, so now what is happening with the condition of M1? How do I know if, or rather, how do I check whether M1 is in saturation or not? Yeah. Yeah, I mean, at least one threshold voltage higher than, I mean, the difference between gate and source could not be more than one threshold voltage. Sorry, gate and drain should not be more than one threshold voltage, right? So now I know both the voltages in terms of threshold voltage overdrives. So essentially, to keep M1 in saturation, just ensure that P2 is greater than right. So this is essentially VS2 is greater than VG1 minus threshold voltage. That is the condition. So this goes. No, this doesn't go there. This goes. So all you have to ensure that the overdrive of M2 is less than the threshold voltage. Why are you not assuming a general VTH? No, you can do that also. There is nothing wrong in doing that, right? So the reason, so the reason I am not doing that is because circuit designers don't think like that. So the way we think is, let's assume that everything is in saturation. Then we figure out what is the limit at which the transistors are in saturation. We start off from there. Then we see margins. Then we say that, okay, at the edge of saturation is probably not a very good way to bias, because if something moves, things will go out. So given that this is where we are, Now, if I have to ensure that, let's say M2 is not at the edge, but 100 millivolt away from the edge, what can I do? Right? So that's how we go about doing it. So this condition that we saw here is essentially to keep M2 at the edge of saturation, right? And M1 also at the edge of saturation. But now, if I have to say that I want to ensure that both M2 and M1 are away from the edge of saturation by certain, let's say 100 millivolt, right? Or whatever value, what should I do? So there are a couple of ways we can approach this, but let's bring in the design variable of VB. Yes. No, if you keep this, if you keep VOV2 to be exactly equal to VTH, then otherwise it will not be. So that essentially gives you the handle of how do I keep M1 away from saturation. I keep VOV2 to be away from lesser than VTH, right? By let's say 100 millivolt or 200 millivolt, then my M1 will be away from saturation. I mean, away from linear region and comfortably in saturation with some margin. So now, now since that is resolved, how do I ensure that M2 is not at the edge? And let's assume now I can change VB. VB is not 2 VTH plus VOV1. What should I do to VB? Should I increase? Should I decrease? Pardon? Correct. So I should decrease VB, right? Exactly. So I should decrease VB. Now, if I let's say decrease VB by 100 millivolt. So I decrease this by 100 millivolt. What will happen? Will the circuit remain as is or something else will change? Exactly. Source voltage VS2 will decrease. Do you see that? It's a constant current bias. I am moving the gate voltage. So the source also has to decrease. Correct? So VS2 will decrease. VS2 will go down by 100 millivolt. So now what is likely to get into trouble? M1 is likely to get into trouble, right? If I don't change the W by L of M2 and just simply decrease the threshold voltage decrease VB by 100 millivolt, the source of M2 is going down, which means my M1 is probably getting into trouble. But I don't want that to happen. So what design variable should I tweak now? Yes, W by L of M2. Exactly, right? So now if I reduce the W by, if I increase the W by L of M2, I am reducing the overdrive of M2. Constant current bias, I mean, again, this equation, right? If I increase the W by L of M2, I'm reducing the drop of VGS2. Which means that I probably now can afford to reduce threshold voltage, reduce VB by 100 millivolt and still keep VS2 same. Right? So if I reduce VB by 100 millivolt and I want to keep the VS2 same, what do I have to do? I have to increase the W by L of M2. If I increase the W by L of M2, this is equivalent to saying I have a fatter pipe and I have a thinner pipe, right? I want to push in the same amount of current. If I want to push in the same amount of current and I don't want too much of pressure, I have to make the pipe fatter. That's all this is, right? So if you have if you are keeping the same amount of current and you want to ensure that the drop across VGS2 is smaller, you have to make the transistor fatter. You have to make the transistor wider so as to, with even small opening, the requisite amount of current can go through. And making the transistor fatter is equivalent to saying I make W by L larger. Okay, does that make sense? Okay, fine. So this is how essentially when you will be designing, right? Not in this particular course, but later on, when you will be designing, this is the thought process that you go through, right? One way, as you said, that you can always sit down and write equations, but that is okay. That is good for problem solving. But if you have to design, you have to start thinking in terms of what happens if this changes, right? What are my knobs? Okay. So this is it. Yeah. Yes. Then you can analyze, definitely. I mean, obviously, when you are given a schematic, Generally, in exams, because of time constraints and whatever, we don't give you open-ended things that multiple solutions are possible. So generally, if I have to give you, if find n constraints, n-1 variables and n variables will be given, or you have to derive in some way that those equations make sense. But you might see that in this tutorial that I had posted, in some cases there is choices to be made, right? I didn't give you explicitly that exactly this is this value. There is probably a range of values from where you'll have to pick. That is a designer's freedom, right? So you can pick any of those values. If you know that certain voltage can be between 100 millivolt to 500 millivolt, you can choose 250, I can choose 300, that's fine. If nothing is given, you can choose any. Okay. But yeah, I mean, typically in exams where you have time limitation and you cannot do that, and also the graders have to grade for all possible solutions, then that becomes a headache. Okay, fine. Any questions regarding this? Yes. How much can I decrease or increase? M2 is going more in saturation, yes. Correct. Yes, right. You can tell me what is the constraint. If I keep on reducing VB, VS2 will decrease, and then what will happen? It is present, right? In the sense that VS2 sets the whether my M1 is in saturation or not, right? So there is a lower limit of VS2, right? So you have to decrease VB so as to not breach the lower limit of VS2. So before, the last thing that I wanted to point out before I move on is, can I change these lower limits of VS2? Is there a design variable that I can tweak to change the lower limit of VS2? So the lower limit of VS2 is set by what? Lower limit of VS2 is set by the fact that the VGS of M1 is certain value, right? But the VGS of M1 is also a design variable, because I can change the VGS of M1 by changing the size of M1. Correct? So that is something that again you can think of, in the sense that if I want to reduce the lower limit of VGS2, I can reduce the VGS1. And I can reduce VGS1 by tweaking the W/L of VGS of M1. Okay. But again, the same, this is all constraint in circulation that can cause M2. If you play that too hard, then M2 can go out of saturation, right? So there is a balance. There is upper and lower limit of both transistors for a range of VB. Okay, fine. And in the assignment, you also saw that this circuit can be modified to make a common source amplifier, right? Let's say I want to push, I want GM times RL times VI across this resistance. What can I do? So this is how it was connected. Okay, so forget about GM times RL times VI. So let's say that I have this VI. What will be the incremental current through the stack? Pardon? There won't be any incremental current, right? There cannot be, because it's a constant current bias, right? There is nowhere this. If there is an incremental current, it has to flow somewhere, right? But the VGS are held constant. which means it cannot flow anywhere. If it cannot flow anywhere, it will not have any incremental current. So regardless of whatever you see, nothing will change. Yeah, correct. Yes. So now if I say that I want to, okay, so now if I say that I want to ensure that there is a, through M2, I want this current to be equal to I naught plus Gm times Vi. This is, let's say I want, right? So let's say we want. What will you do to ensure that this happens? Pardon? Where? Okay, so his solution is connected large capacitor here to ground. Okay, so what will happen? Why do you say that the incremental current will be this? Fine. So that capacitor will get shorted. It's equivalent to M1 is getting shorted. M1 gate of M1 is getting shorted. Fine. So why I still don't understand why should the incremental current through M2 be Gm times Vi? See, the incremental current through any transistor is Gm times VGS. Correct? So Vg is Vi in this case. So if I want the incremental current to be Gm times Vi, then what should I do to the source? Right. So since my current is incremental current is Gm times VGS, and Vg is in this case Vi, if I want incremental current of Gm times Vi, incrementally the source should be shorted. No, in this particular case, it's not, right? But let's say we want this, then we have to see what can we do. Correct. Exactly, right? So what we can add to this circuit. So if I want this, which means that I want this to be 0. In this case, this is VG2, VS2. Okay, so how can I make the incrementally, short M2? I can add, I mean, we only have, till now we have only learned about one way of realistically shorting any node. Basically add an infinitely large capacitor to that node to ground, right? So I'll just add C2 and assume C2 is large enough. If C2 is large enough, then any incremental current, this Gm times Vi will flow through this into the short that is being imposed by C2. And the quiescent current anyway flows through M1 and M2. Okay. So in pictorial terms, this voltage will be VB plus a sinusoid. No, VB plus a sinusoid, which is Vi. Yes. Right. Why is drain of the M2 is open? Correct. Fine. Fine. Why not? No. So okay. So see. Correct. I agree with what you were saying. Yeah. So I made a blunder here. You are right. So essentially what I said was, if I only concentrated on this part, correct? So essentially what his argument is, and it's a right argument, that if this current has to be incrementally has to be Gm times Vi, so I can see that this current can go out through the source, but that current should also come in from the top, correct? So there should be a current that should come in here, right? It's a loop ultimately. If I am drawing current out, there should be something that flows in, right? Indeed, that is correct. That's a very good observation, and I made that blunder here. So, which means that I have to give it some path. I have to give it some path to flow in. So, how can I give a path for it to flow in? I can again connect a capacitor, and this, I mean the initial solution will do. So, if I take capacitor to ground, so this current will now, incremental current will flow into this, right? And the ground is connected, right? So I have a loop in place. Okay, so now if I want, and this current will be, I know this current will be GM times VI. This current will be GM times VI. Now, if I want GM times VI times R, right, or rather GM2 times VI times R. Correct. Yeah. Correct. Yes. So if I want to now get a common source amplifier kind of functionality, what should I do? Take that R and what should I do? Yeah, place it anywhere in the loop, essentially, right? Anywhere in the loop, and observe the voltage across that R. Or in other words, in this case, I can say that I will do this. So this is RL. The voltage that will accrue across RL is GM2 times VI times RL. Okay, so this voltage will be GM2 times VI times RL, right? Negative if I, the way I have sketched the polarities. Right? Make sense? Okay, great. So this is essentially one of the problem statements that you have. You have the solution. Yes. You are talking about the last one. Yeah, fourth one you can do that. You don't know, no, nothing is real. All these things are not required. I didn't give you any constant on the fourth one, right? You can use the initial one, no issue. So this is, I think, was the one where question 2 or 3 was this, right? Yeah. Okay, great. So now this particular circuit falls in the category of feeding the current into the drain and tweaking the source, right? So we have done feeding the current into the drain, tweaking the gate. We have done taking current out of source, tweaking the source. This was the scenario where we were feeding current into drain and tweaking the source. So the last one that remains is take current out of source and tweak the gate. Yeah. So the last one. Okay. So the last one was I will pull current out of the source and I will tweak the gate. Okay. And by that very definition, I am saying that I am not going to do anything to the drain. Let's keep it VDD. So now, what is the argument? Let's say this is M1. This is M1, and I want to ensure that I have to do something to the gate of M1 in order to ensure that M1 is biased properly, right? So what will the argument be? Walk me through the argument. Let's assume this current is ID1, and let's assume if ID1 is less than I0, what's going to happen? Pardon? Yes. So if ID1 is less than I0, no, right? So if, which means that what? If it's a Vs, let's say it's not Vs2, Vs. So if ID1 is less than I0, then I'm pulling out more current than I'm pushing in. So Vs should decrease. Oh, you said decrease. Okay, fine. So Vs should decrease. If Vs decreases, it auto biases, but I don't want to be constant with only changing Vs. I want to change gate voltage, right? So what should I do to the gate? I should increase the gate. Okay. So how do I? So I have to observe the source voltage and I have to take action of the gate. So when source voltage decreases, I have to increase the gate of M1. So I have to connect something here where if this decreases, this increases. Right? So do you know of anything that can do that? If an input voltage decreases, output voltage increases, what kind of simplistic thing that you can think of? Battery is not, right. Battery is goes in the same direction. Yes. What is that? What do you know of any 180-degree phase shift amplifier? I mean, obviously, in the context of whatever you have done in this class, in this course. I can't hear you. Okay. Okay, I can do something with the resistor, that is fine. Yeah, so how do I make that arrangement, right? So if one side increases, the other side decreases. Yeah, a common source amplifier, right? 180-degree phase shift. If input increases, output decreases. Right? So I can stick in a common source amplifier there. I mean, I haven't yet really said that it has to be at the same, relationship between Vs and the Vg has to be equal to 1. It can be anything. We have to see what it can be. Right? Not necessarily it has to be 1. It can be anything. Then we have to go and figure out what it is. Yes. Okay, so what is this argument? If ID1 is less than I0, right, Vs is decreasing. So which means that while one might argue that it is getting auto bias, but we are not particularly bothered about what's happening to the Vs. What can I do to Vg to ensure that things are in, the transistor is able to push in that much amount of current? I should increase Vs. Means this implies we should increase Vs. Sorry, Vg. Yeah, it is auto bias, but it's auto bias under the constraint that Vs moves. But let's assume that we don't want Vs to move. You will see why in the next class. So let's assume that we don't want Vs to move. But is there another handle? Vg is the handle, right? So if so what is the handle now? I have to increase Vg, right? So that's what we are trying to do, right? So you replace this with okay. So this is what it looks like. I just connected it, but I haven't really analyzed whether it will be in saturation. Both the transistors will be in saturation. What will be the relationship between Vs and Vg of M1? I haven't done any of these things. So you just put it there. Then we have to see what actually what's actually going to happen. Okay. So let's do that. So now, without going into the mathematical details in this class, what do you think? How do you go about figuring out whether both the transistors are in saturation? Assume it in saturation and then find out the constant, right? So I will start off with, let's say this is Vs. Okay. For this is Vs, what will be the gate voltage of M1? You assume W by L to be equal to start off. What will be the gate voltage of M1? Yeah, right. So this voltage will be Vs plus VGS of M1, which is threshold voltage plus V over drive of M1. Right. So if that is the case, what will be the current through this resistor? VDD minus that. You mean this one? So you know the current. You know the current I0. Since you know the current I0, you know the VGS. Right? And I assume certain Vs symbolically, which means that my VG will be Vs plus VGS. Right? That's all. Here Vs is unknown, but VGS is known. Because if you assume certain W by L, you know the current, so VGS is known. Yes. Yeah, true. VDD is a design variable, but given certain VDD, whether the solution exists. VD2, yeah. Okay. So let's see. Okay. So now now you have everything in terms of Vs, correct? So how do you figure out Vs? So you equate this current. What is this current? This current is whatever you found, right? VDD minus Vs minus threshold voltage minus V over drive by RD2. This will be equal to the current through M2. And current through M2 is half mu n Cox. Okay. So now once you equate this, you know the value of Vs. If you know the value of Vs, then you know the value of Vg1. And once you know these two constants, you know whether the transistors are in saturation or not. Yes. Yeah. So you equate these two expressions, right? You equate this expression and this expression, then you get Vs. Correct? So once you know Vs, you essentially know both the node voltages, right? So if you know Vs, you know Vg. So if you know Vs and Vg, you know the condition on M2. Correct? And the way I have hooked M1 up, looks like M1 will always be in saturation. Correct? The drain voltage is connected at VDD, and Vg1 cannot ever go beyond VDD. Right? So M1 I don't have to bother. So I have to bother about M2. Right? So M2, if I know Vg1 and I know Vs, then M2, I know whether it's in saturation or not. Yes? Why? Okay, so can you, so his question is, this looks like, so this looks like always to be greater than or equal to Vs minus threshold voltage, right? Yeah. So is the scenario not necessarily now, right? So you have still a design variable of V over drive 1. You can choose a bad V over drive 1 to nullify. No, V over drive 1 cannot be negative, right? V over drive 1 is positive, right? Correct. Yes, I agree with you. Right? So it seems like this is always in saturation, and which it might as well be. Correct. Yes, you can. Yes, you can. Is that what it is? Correct. Correct. Yes. So now his argument is correct, and I should have pointed this out earlier in the sense that if you have to keep M1, so these two voltages, VG1 is always greater than VS. Correct. VG1 has to be always greater than VS. If VG1 needs always to be greater than VS, then M2 cannot go out of saturation. Correct. So that is actually a good observation. You need not even do the math. Okay. So essentially your VG1 is because of M1, the current through M1 is finite. VG1 of VGS of M1 will be greater than 0 or greater than threshold voltage. So which means that VG1 of M1 is always greater than VS, which essentially means that now if I switch my attention to M2, my M2 is always in saturation. Okay. So now the question is, what is the who is setting the bias, in the sense that if I change I0 by slight amount, will VS change appreciably or will VG change appreciably? If VG changes appreciably, then I can say that this is the situation where I have changed I0, and the significant change in VG is what is setting is actually the feedback. In the sense that if I have, we started off saying that this is a condition in which if I change, the bias is getting set by observing the source voltage and tweaking the gate voltage. But as we pointed out, it seems like both source and gate voltage can change. If I change I0, right? If I change, let's say I0, yeah, let's do that. So let's assume that this current was I0 and it changed to I0 plus delta I0. Okay, so which means that let's assume there is an incremental current of I0, delta I0 this way. Okay, this is equivalent to saying my I0 changed from I0 to I0 minus delta I0. So if this happens, what is likely to happen to this source voltage? Incrementally, it's supposed to increase, right? I'm pushing current in, so this is supposed to increase. Let's say this increased by Vs. Okay, if this increased by Vs, what's going to happen to the gate voltage of M1? Yes. Yes, but by how much? No, right? I mean, why? So what is the relationship between these two nodes? Exactly, right? So it will be not something, it will be exactly that, right? So your rate of change of change in VG and VS are related by what? This is the gain stage. This is the common source stage. GM2 times RD, isn't it? So this stuff over here, you can think of, you can just forget about the stuff that is connected. So you can just, if this is VS, this is VG of VG1. So what will be the relationship, incremental relationship between VS and VG1? So this will be not approximately, even exactly equal to minus GM2 RD times VS. Assuming it's in saturation, and that's what we argued, that this will be in saturation. Right? Does that make sense? I see some confused faces. So, okay. So forget about everything that we that we see here, right? So only concentrate here. We'll come there. We'll come there. Oh, the bells are not audible. So, do you have another class? Right away. Do you have another class? Okay, so give me 1 minute, then you can go. So, do you agree that the stuff that you see here is a common source amplifier? If that is a common source amplifier, the gate of the common source amplifier is going by Vs. What will be the drain of the common source amplifier go by? Right, minus Gm2 RT times Vs, right? So if that is the case, then that's what I am essentially doing here, right? So if this voltage increases, by certain amount, this voltage will decrease by a bigger amount, right? So in other words, when I am trying to push it, the way I have drawn the incremental circuit, in the total sense, I am trying to reduce the current, right? I'm trying to reduce the current through M1. If I am trying to reduce the current through M1, I have to decrease VGS through M1. So decreasing VGS through M1 can be done in one of three ways. You either decrease VS, or you either increase VS, or you decrease VG, or you do both. A combination of both. So in this case, it looks like we are doing a combination of both, right? But can you comment on which one will change more? Will the VS increase more or VG decrease more? VG will decrease more if you can ensure that Gm2 times RT is much greater than 1. So in an incremental sense, one might argue that if Gm2 times RT is much greater than 1, only VG is changing and VS is not changing. Yes, right? So that's what we are essentially after. So in an incremental sense, VS is a short circuit, effectively. VS is a virtual ground. Because you change I0, it looks like all the heavy lifting of adjustment of current is being done by the gate, while source is not moving. Right? You are pushing in current and you are seeing the voltage is not changing, which means it's a virtual ground. It's not an actual ground. It's not connected to any hard ground, but you are pushing in current and you are not seeing the voltage move, which means it's an incremental short. Okay. Okay, fine. Let's stop here.